So here V1 minus 0 is equal to IR. That's the first equation. The second equation, look, this is the direction of current. So 0 is at a higher potential, V0 is at a lower potential. So 0 minus V0 is equal I into RF. This is RI. Now this is our second equation. Just divide the second by the first. Then we have Vi over minus V0 is equal Ri over Rf. That means V0 is equal minus Rf over Ri into Vi. But we know that V0 is equal minus V0 is equal A times Vi. Therefore, but V0 is equal to this. Therefore, A is equal minus Rf over Ri. Okay. Got it. How we got this equation? If you know how we derive this equation, it will be easy. Is it clear? The mode we derive the equation. Then let's look at, have you noted? So next topic, non-inverting amplifier. For non-inverting amplifier, for which terminal should I give the input? Positive or negative? We have to give the input to the positive terminal. Anyhow, we will have a negative feedback. Negative feedback is necessary. The feedback resistor. And this is connected to ground. So this is the output. And this is our input. So here again, this is RF, and I'll consider this one to be R. Again, it is in negative feedback and closed loop. Therefore, the golden rules are applicable. In the golden rules, they say the potential difference between these two terminals is 0. this has a potential of Vi. Therefore, over here also we have the same potential Vi. Oh, I'll take this point. Over here also we have the same potential Vi. Draw this resistor slightly below. Now this point has potential Vi, that is due to golden rule 1. In golden rule 2, here you will have a current flow. You will have a certain current flow. During that current flow, there won't be. Now this is non-inverting, right? If you give positive potential, you will also get the output in the positive uh, potential, and it is going to be larger. Therefore, current will flow in this direction. This is the direction of current flow. And here, through this resistor, also you have the same current flow because the current won't enter through the input terminals. So that is important. The direction you mark the current is really important. That is how you get the equation properly. Now, this voltage is V0. Using Ohm's law, we can write V0 minus Vi is equal V0 minus Vi is equal I into Rf. And again, I can write straight away from here all the way up to here. From here to here, what's the potential difference? It is V0 minus 0, which is equal I into Rf plus R. So this is my first equation, and this is my second equation. Just divide them. When you divide, I'll divide the second equation by the first equation. When I do that, I have V0 over V0 minus Vi. I'll divide the other way. 1 over 2. 1 over 2, I have V0 minus Vi over V0 equal Rf over Rf plus R. Now here, I can write they must separate denominators. So I get 1 minus Vi over V0 is equal Rf over R plus Rf. Now my aim is to somehow get this, somehow subject V0. For that, I will just shift their side. I'll bring this to the right and this to this left. So we have Vi over V0 is equal 1 minus Rf over R plus Rf. This is equal, just simplify. When you simplify, you get R over R plus Rf. Am I right? Yeah. So, we need V0. If I subject V0, V0 is equal, you will have to cross it. V0 is equal R over, no, R plus Rf over R into Vi. So we get V0 is equal Rf over R plus 1 into Vi. Okay. So we know that V0 is equal A times V1, sorry, A times Vi. A is equal 1 plus Rf over R. Okay. Are these 2 equations clear? These two equations clear? Okay, so we know that V0 is equal A times V1, sorry, A times Vi. A is equal 1 plus Rf over R. Okay. Are these 2 equations clear? 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 Now, what is the difference between open loop and closed loop? In open loop, for A, we straight away got a value. But look here, for inverting amplifier, for A, we got a ratio. That is also the ratio between the resistance of the forward bias and the input resistor. Again, for non-inverting, also we got a similar equation. That means you are able to control the gain. You can control the gain by controlling the resistors. In case of open loop, did you have a control of the gain? No, it was always infinity. But in case of negative feedback, when we have a negative feedback, we are able to get a control of the gain. That is why we are able to use the negative feedback as an amplifier, negative feedback configuration as an amplifier. So you must know whether it's inverting or non-inverting. Look, from A itself you can understand. For inverting, you're getting a negative in front, but for non-inverting, you're not getting a negative in front. Now, how does this negative feedback actually help this operational amplifier to work as an amplifier? So what I'm going to tell now is something extra, so you don't need to know it, but if you know that idea, it would be much better. Okay, so just listen. Now let's consider this inverting case. In the inverting situation, now I provide a signal, an input signal, let's say a sinusoidal one. Now remember, in which region can the operational amplifier work as an amplifier? Only in the linear region. So somehow I must bring my input voltage. So this is the input now. Somehow I must bring my input voltage into this region. Okay, I must bring it back into this region. So let's see how we can do that. Now we provide a signal, something like this, a sinusoidal signal. Now, when this signal, so this is the voltage over here, when this signal passes, the current is going to flow in this direction. When it comes over here, the potential would have dropped slightly, right? It would have dropped slightly. And when it goes over here, this is an amplifier, okay? This is an amplifier. It will amplify the signal. It will amplify the signal, but it is a inverting amplifier. Therefore, the signal gets inverted and amplified. Okay, the signal gets inverted and amplified. Now, again, I'll repeat the sequence. First, we provide a signal. When it is passing this resistor, potential drops. Therefore, this signal turns into a signal something like this. Still, it is large enough to saturate, because to saturate, we only needed 150 microvolt. So still this is large enough to saturate. Then it goes through this operational amplifier and it gets amplified. Now when it is getting amplified, it is inverted. through this resistor, through this feedback resistor, it comes over here. This time it will reduce because it is passing through a resistor. But look how these two waves meet. These two waves, when they meet each other, will they undergo constructive interference or destructive interference? What type of interference will they undergo? Constructive or destructive? So the waves are 180 degrees out of phase. If they are in the same direction, they will undergo constructive, but here it's destructive. So when they undergo destructive, if they are perfectly equal, it will become zero. But there might be slight differences, right? There might be slight differences between these two. So we will get a resultant wave which is very small, but it has the same similar shape. Now, when it cancels, still it will have this similar shape, similar to the initial. Okay, so it gets a similar shape, but this wave would have initially saturated this operational amplifier. But going through this process, it forms a resultant wave, something like this, which will fall within this region. During negative feedback, this region also gets broadened. Okay, this region also gets broadened. Like now we can control the gain. So this region also gets broadened, something like this. And at the same time, by controlling these two resistors, we can broaden. At the same time, now this wave, due to these procedures, this wave also falls back into this region. Got it? So by now, you should have got the reason why we say the potential difference between these two terminals is 0. Why delta V is equal to 0? It is actually not 0. It is actually almost equal to 0. The golden rule number 1. By now itself, you should have understood. These two undergo destructive interference. We get a small wave. So that small wave doesn't have much difference between these two. There is no much difference between these two terminals, where it is almost equal to 0. Is that idea clear? You don't need to know this one in detail. For now itself, if you understood, there is some process going behind, that's fine. Then how about non-inverting? So in the inverting, what is happening? At the same point, two waves of different phase meet each other to cancel and fall back into this region. In non-inverting, something else happens. So let's get the non-inverting. So this is the non-inverting terminal, sorry, non-inverting amplifier. So here we provide the input to this terminal, small input. When it goes through this amplifier, it gets amplified a lot, a larger wave. And when it goes through this feedback resistor, now it becomes a smaller wave. Okay, it becomes a smaller wave. but its direction didn't change. Remember, its direction didn't change because it is non-inverting. Still, look, when you get the potential difference between these two, delta V, you will have to deduct this point from this point, this point from this point. So from corresponding points, you will deduct. So when you do that, what can you tell about delta V? Both of them are similar, and there is only a slight difference between those two. Therefore, delta V is this time also almost equal to 0. Agree? In the previous case, both the waves met at a point to undergo constructive or destructive interference. Here, they do not meet at a single node. Instead, they are on two different terminals. One of them is in the non-inverting terminal, which undergoes amplification, and through the feedback resistor, a very similar wave is given to the non-inverting terminal. So when you get the difference between them, there is a very small difference. Got it? So you don't need to note this. It is only an extra point. And in addition to that, how does the current flow in a operational amplifier? An operational amplifier, let's think about the open loop. Now you must be able to understand what is plus VC and what is minus VCC, right? Can you remember the circuit? We had a battery. In the battery, the center was Earth. Okay, this center is Earth. Here, let's say we have a green LED, and here we have a red LED. We have a green LED and a red LED. So let's say this is 10 volt and this is also 10 volt. Now, if V1 is greater than V2, what will happen is the current will flow in this circuit from this 10 volt battery. The current will get into the operational amplifier through plus VCC and go through this diode back to the battery. Okay, if V2 is greater than V1, If it is the opposite, now the operational amplifier will receive current like this. It will get out of VCC minus VCC and get back to the battery. So the input terminal, there is no current through the input terminal. Through the input terminal, there won't be much current. There might be small current. Other than that, there is no much current. So what this input terminal does is, input terminal will compare which one is larger. If V1 is larger, it will connect this plus VCC circuit. If V2 is larger, it will connect the minus VCC circuit. So it is just like what do you call? Um, just like a controller or a regulator, just like a regulator. By comparing the voltage, it will either connect the plus VCC circuit or it will connect the minus VCC circuit. Did you get the idea? Did you get the idea about the power supply, how it works? So there are some questions related to this operational amplifier in your past paper also, the MCQs. Try those questions. Here under inverting amplifier, under inverting amplifier, draw like this. When you give a wave like this, small wave, the output, you get a large wave but inverted. The wave that was on the bottom gets to the top. But for non-inverting, when you give a signal, you get the output in the same phase. Done. Inshallah, by next class or the coming next after the next class, we will be able to finish off electronics. Have you noted these two diagrams? So with that, we finish off operational amplifier. Hope the idea of operational amplifier was clear.